All right, so our first topic in our third unit of chemical systems in equilibrium is called dynamic equilibrium in chemical systems. So what we're actually going to be studying in this unit is reversible chemical reactions, and we're going to look at the concentrations of reactants and products and note sort of how they change over time. So that's what equilibrium is all about. It's about looking at dynamic equilibrium in this case, so that means ever changing in chemical systems. So what does that actually look like? All right, let's take a look at this slide. So it is dynamic, that means it's in constant motion. And it's reversible, which means it can be approached from either direction. So I can start with only reactants and make some products. I can even start with only products and make reactants. After a period of time, the reactants and products are constant. Doesn't mean that they're equal, it just means that their concentrations are staying constant. That means that the forward, which is the left to right, and the reverse reactions, right to left, occur at equal rates. They're occurring at sort of the same speed. So if you take a look at this graph, I added a few things on there, so you can add that into your notes if you would like. You can see up at the top, there's an R, that's sort of your starting with your reactants in red. And then at the bottom, we've got a P showing your products being formed. So if you look at sort of time zero, so if I sort of redraw this in so you can see where I'm focusing in on. If I look right here at time zero, I'm starting off with 0 products, right? That's at 0. And I'm starting off with a certain concentration of reactants. As the reaction progresses, obviously the concentration of my reactants is going to start to drop. Why? Because I'm using up my reactants to make products. So then when I look at the concentration of products as the reaction starts, my reaction of products increases. So that is sort of not new for you guys. The part that's new in this course is going to be later on. After a little bit of time, the rate of the reverse reaction and the rate of the forward reaction are going to remain constant. Now here's an example where the concentrations actually stay the same. You can see both lines sort of meet at the same spot. Okay? But this doesn't mean that the reaction stops. So if you look at our next point, it says the forward and reverse reactions continue after equilibrium is obtained. So we don't look at whether or not it stops when we hit equilibrium, but we just know that when something hits equilibrium, your forward rate is going to equal your reverse rate, or the formation of reactants is going to equal the formation of products, okay? This always has to happen in a closed system, which means that matter cannot leave or enter the system. So that is something that we have to take into account when we're doing a lab. Oops. So next, it says types of equilibria. This is the first one. It's solubility equilibrium. So we're looking at when something dissolves in water, solubility. This is reached when the concentration of the dissolved solute is constant, and it must contain both dissolved and undissolved solute at the same time. So most often than not, when we're talking about these types of equilibria, we look at things that are either almost at a saturated point, or an equilibrium or a compound that doesn't dissolve very well in water. So I'm just going to, I don't think my link here works. Open? No. Okay, so I'll have to select it from my actual file. Let me just grab that. Oops. And I'm just going to, oh, I can't seem to be able to control the volume on here. So we'll just start it, and hopefully it won't be too loud for you. So here we go. We're actually going to look at the solubility of silver chloride when we try to dissolve it in water. This might get loud, sorry. I know, it's very high tech. Okay, so here's silver chloride. You can see when it dissolves in water, some of the ions break off the solid crystal and are floating around in water. What is new for this course is that some of them will actually come back together and reform in the solid. Now the interesting part here is this will always continue to happen. So it's not that the dissolving ever stops. and remain stagnant. It's just that your formation of the ions or your formation of the solid crystal, those rates remain constant, and your concentrations of your reactants and your products will remain constant over time. So this is going to basically continue to happen. So right now the system is at equilibrium. There we go, all done. So there's my equilibrium equation for silver chloride, okay? So we'll go back to the slides now. If we look at just the last point, the rate of dissolving has to equal the rate of crystallization. So you can see that in an equilibrium phase, we're looking at something that's going to constantly be changing, so it's going to be dynamic, but your rates of your forward reaction, so in this case dissolving, has to equal the rate of your reverse reaction. All right, another type of equilibria is a phase equilibrium. So this, again, has to happen in a closed system. And it looks at evaporation and condensation in particular. That's sort of our easiest way to measure this one. So at equilibrium, the pressure of gas remains constant. A solid liquid equilibrium we can also do that. It's a little bit harder to measure, but we can still do it in the lab. So we're looking at basically in phase equilibrium, we're looking at the change of state. So in my picture here, I have something that's entirely in the liquid form. And then as you can see over time, some of the molecules will evaporate off and become a gas. Once it hits equilibrium, that means that your formation of a gas at the top up here is going to equal the formation of recondensing back into a liquid. That's a phase equilibrium. So same thing with solids and liquids, except you have, at the freezing point, you've got melting and freezing happening at the same time. So it's going from a solid to a liquid instead of from a liquid to a gas. Last type of equilibrium we're going to look at today is chemical reaction equilibrium. So these are quantitative reactions. That means we can actually measure some numbers from these, and we're actually going to start to do some calculations. So when a chemical reaction proceeds to completion in an open system, molecules are free to leave the system, which prevents the reverse reactions from happening. Then we have a quantitative reaction. That's basically what you guys did in grade 11. This year, though, we're going to look at equilibrium. So if we keep the system closed, and that basically means exactly what it sounds like. To close a system means that nothing can escape it and nothing can enter it. So we actually have to put a stopper on your test tube or put it in a flask with a lid on it. Anything like that has to be closed so that things can't completely leave the system. Here's an example. N2O4 is actually colorless in that form of a gas. So that's actually what we're looking at here. If we add heat to it, it actually turns brown because the reaction actually changes. So it's difficult to see in these pictures, but you can kind of see how over here, this is sort of a lighter brown than over here. So this is a flask that's been heated, and therefore we have only NO2 in there. Here's a flask that's tried to be cooled down, so we're starting to get to the colorless point. So you can see how we can start to measure how much reactants or how much products are being formed based on the color. So, reversible reactions. An equilibrium will have the same composition whether approached from reactants or pure products. So this is an example taken straight from your textbook. And here I'm basically showing you that same equilibrium with N2O4 and NO2. Here I start with only reactants and no products. And you can see over time your reactants decrease because some of them are being formed into products, and your concentration of products increases. But over time, they start to eventually plateau off, and the concentrations of each remain stable. Doesn't necessarily mean that the concentrations are equal, because look here, off my graph, my concentration of N2O4 is probably about 0.36. And my concentration for NO2 is about like 0.13 or 12. So the concentrations themselves, that's your moles per liter, don't have to be equal. They just have to be constant. That's the key word here. If we take the same reaction, but we start with only products and no reactants, the same thing is going to happen because it is a reversible reaction. Your concentration of products is drastically going to drop at the start, and your reactants is going to increase. But over time, again, you're going to plateau out, you're going to balance out, and you're going to hit the exact same concentration at about 0.36 and about 0.1, what did I say, 3. So that's what I mean at the top when it says that it will have the same composition or the same concentration, whether approached from only reactants or only products. What does that mean? That means it doesn't matter where you start. It doesn't matter what your concentration of reactants or products are when you start. The part that we've got to calculate is what happens at equilibrium, and I'm going to show you how to do that. The first way to do it is the percent reaction at chemical equilibrium. This is not the most common way, but it is important. So we're going to take a look at it quickly. This is a state of equilibrium, can be described in two ways. So the first, percentage equilibrium or percentage reaction, is the yield of product measured at equilibrium compared with the maximum possible yield of product. Okay, so when we're doing percent reaction, we're always looking at product. The second one is an equilibrium constant, and that's going to be what we're going to look at in our next video. So let's take a look at just a percentage reaction. Here's a hydrogen iodine system at 448 degrees Celsius. So there's my reaction. I've got hydrogen gas and iodine gas, and it can form hydrogen iodide or hydroiodic acid. Okay, and this reaction is reversible. So in each system, I start off with a different concentration of reactants and products. So let's say this is my first trial or my first system. You can see I started off with only reactants and 0 products. In my second system, I started off with less reactants and more products. And then in my third system, I started off with no reactants and only products. When each of these systems hit equilibrium, you can see the concentrations are not necessarily the same, but they are constant. Okay, and they're actually constant based on how much we started with, in the sense that it has to do with actual quantities. So equilibrium systems, you can see that these two are still equal. Again, if you go back to stoichiometry, because they're in a 1-to-1 ratio. Okay, these two are the same and these two are the same, okay? And your concentration of hydrogen iodide changes, okay? So when we measured this and when we found to be at equilibrium, these were the numbers that we got. At this point, don't worry about where the numbers came from. Just sort of pretend like we did a lab and we got these numbers for concentration. Now, what do we do with them? For experiment 1, so you guys have this in front of you still because you have your notes. So we're going to look at this row. So for experiment 1, your percent reaction is the actual product yield divided by the theoretical product yield times 100%. So if I go back, my actual product yield is 1.56. So that's what went up on top. At the bottom, I put 2 moles. That's because if I start off with 1 mole of hydrogen and 1 mole of iodine, I should make double, based on stoichiometric calculations, of hydrogen iodide. So that's what I did here at the bottom. I did a quick stoichiometry calculation. So I started off with millimoles per liter of H2, and I multiplied it by 2/1 because that was what was in my balanced chemical reaction. So that's how I got, if all of my reactants, and if I had 0 reactants and all products, I should get 2.00 millimoles per liter of HI. So when I divide those two numbers back up here, I get 78%. So 78% of the reaction actually made products. What does that mean? That means we're in this category. So let's take a look at this chart. I'm greater than 50% products, so that means products are favored. That means I'm going to make more products than reactants. If I'm less than 50%, that means reactants are favored, and I'm going to have more reactants than products. If I'm less than 1%, that means it's no reaction, and I have all reactants. If I have greater than 99%, that's a quantitative reaction. That's the stuff you guys looked at in grade 11. You assumed that all reactants converted to products. All right, so some stoichiometric calculations for reversible reactions, okay? An ICE chart, initial change equilibrium concentrations chart, is used to calculate the concentrations of reactants and products at equilibrium. So it says, how are we going to actually get those numbers that I got on the example? ICE chart, this is going to be your new best friend. You're going to be using this pretty much for every question in this unit. So don't be lazy, draw them out and actually fill it in. It will help you. So here's what happened at this equilibrium. I had 0.1 millimoles or moles per liter of H2 starting. I had 0.1 moles of I2 starting, and I had 0 products. I don't know what the change is going to be, but I know that because I have no products, I'm going to decrease my reactants by some number. We're going to call it X. And my products are going to increase by a value of 2X, again, because I have a 2 in my balanced chemical reaction. So when I calculate my equilibrium concentrations, it's going to be 0.1 minus X for H2, and 0.1 minus X for I2, and then 0 plus 2X, or just 2X, for my products. So if we go through an example of this, let's see if we can fill in our ICE chart. So consider the following reaction. So this is a hydrogen and a fluorine making HF. So if the reaction begins with 1 mole per liter concentrations of H2 and F2, sorry, and 0, no HF, calculate the concentrations of H2 and HF at equilibrium if the equilibrium concentration of F2 is measured to be 0.24 moles per liter. So what I've done, I've put in my reaction up at the top. So in the first row over here, you put in your reaction. H2 plus F2 gives you 2HF. My initial concentrations, these are usually given to you in the question, unless I'm going to ask you to work backwards. So this is what's given. So I said it was 1 mole per liter for each of them. So I put that down there. And I said no HF to start with. So that's why I put a 0 in this column over here. All right, so then I read the rest of my question. Calculate the concentrations of H2 and HF at equilibrium if the equilibrium concentration of F2 is measured to be 0.24 moles per liter. So this is at equilibrium. So I put that there. Since the H2 and the F2 are both on my reactant side and they're both a 1-to-1 ratio, I know that my equilibrium concentration of H2 is exactly the same. So that's why I put 0.24 there without even doing a calculation. So that's sort of, I think, my next. Oops, sorry, I thought I had the answers at the bottom there. So now basically the question is how much of this is made. So this is where I have to fill in my second row, the change in concentration. And it's going to go up by a factor that I don't know yet, okay? But I do know that H2 is going to decrease by a value of X. My F2 is going to, also decrease by a value of X. And because there's a 2 in front here, this is going to go up by a value of 2X. So if I can solve for X here and here, and then multiply it by 2 over here, I can figure out what my final concentration is for my HF. Sorry, I'll just put that back in, plus 2X. So, if it was in the question that 1.00 minus X equals 0.24, that's basically this whole column here, then I can figure out that X is 0.76. So now that I know that, I can plug that number in up here. So 2 times 0.76, that gives me my answer, which is what I'm looking for here, 1.52 moles per liter. So in my last statement, the concentration of H2 is 0.24, the same as F2. And the concentration of HF is 52 molar when the system reaches equilibrium. Example number 2, this comes off of page 435 of your textbook. We're going to do the same thing again. So this time what I'd like you to do is try to pause the video. I'll tell you when, and try to see if you can come up with this on your own. So when ammonia is heated, it decomposes into nitrogen gas and hydrogen gas according to the following equation. So I've given you the reaction there. When 4 moles of NH3 is introduced into a 2-liter rigid container and heated to a particular temperature, the amount of ammonia changes to 2 moles. Determine the equilibrium concentrations of the other 2 entities. So I'm going to give you the ice chart here. First off, you have to understand that your initial concentration of NH3 is in a 2-liter container. So I've given you moles and liters. You have to divide the two. Remember your C equals N over V equation to get concentration. So that's how I get that my initial concentration of NH3 is 2 moles per liter. So once you have that, and then you can also figure out your concentration of NH3 at equilibrium because it's gone down to 2 moles. So same thing goes there. So now if I set up my ice chart, there it is. So again, I started off with 2 liters of ammonia and no products. And I know at equilibrium, my concentration went down by X to 1. So using that information, can you calculate the concentrations of the other 2 entities? What's the concentration of N2 and what's the concentration of H2? So if you want to pause it and try and figure this out now, go to town. Okay, we're going to go through the answer. So now your answer looks like this. So what you have to keep in mind is your coefficients from your balanced chemical equation. So we've got a 2 and a 1 and a 3. So when this actually went down, it didn't go down by X, it went down by 2X. So basically 2 minus 2X equals 1. So if you flip this around and you actually solve for X, you can see that X is 0.5. What happened to my N2 and my H2? Well, my N2 started off as 0. It's going to go up by 1x. My H2 is going to go up by 3x. So this is going to be 0 plus 3x, which is 0.5, or 0 plus x, sorry, which is 0.5, and this is going to be plus 3x, which is 1.5. So there's your quick answer. If you have any other questions, we'll take them up in class, and I'll see you guys there.